when it's live. Okay. I don't see it on the YouTube website. Okay. Good afternoon, everyone. Welcome and thank you all for joining the third forum of the NUS Architecture Online Grad Show Intersection series, titled Thinking, Computing and Designing Space. Before we start, I would like to express our warm welcome to our esteemed guest speakers today, Dr. Patrick Jensen, Mr. Pan Yi-chen, and Mr. Vignesh Kaushik, who will be joining us in a short while. As well as our student speaker, Anders Ang, April Zhu Weijie, and Lip Jiang, who will be sharing with us their thesis projects. My name is Yu Qing, and I will be the moderator of today's session. First of all, I would like to give a brief introduction on our cluster under the theme technology. Architecture cannot be divorced from the techniques which form it, from orthographic drawings to computer-aided design tools, to computational design methods and VR worlds. The methods of making architecture have constantly evolved, and the worlds that architects design also include the virtual realm that an increasing number of digital natives are beginning to inhabit. The works of this cluster harness the prowess of technologies in multiple manners. Firstly, as posited in Kapos, the second digital turn, technology is no longer just a tool for making, but rather a method of thinking. Computational methods can be used to optimize urban connections, wayfinding methods, structural efficiencies, and myriad of other parameters. The thesis thus attempt to unwind and process the complexities of today's world, reordering them architecturally into both practical and aesthetic designs. Secondly, architecture design has to respond quickly to advancements in technology. Multiple theses envision standard programs and urbanities disrupted by new media platforms and production methods, thus responding spatially through VR realms or physical programs augmented by technology. The thesis of this cluster thus attempt to reimagine the architect in this data-driven interconnected world. While technology's evolution may occur at an ever-accelerating pace, the works respond to the zeitgeist of the 21st century and the increasing blend between the digital, the material, and the architectural. In this cluster, students' thesis works can fall into a few areas. First of all, Joey, Anders, Yuqing, and Chi-Sin's project use technology at urban scale. Various computational techniques and ideologies are used to study mobility, data, behavior, and form for the betterment of city. Second, technology is used at component scale by Lip, Dan, and Wenda, where they look into urban farming, architectural components, and facade with the aid of computational tools. April and Weijie shows their responses towards a technology-driven future world with the focus on artificial intelligence and digital footprints. Next, Ziwei, Thomas, and Matthew shows their spatial strategies through VR and physical programs augmented by technology, and Derek and Anna explored new types of participatory design with the aid of computational techniques and methodologies in creating urban and residential spaces. You can also explore more on Matthew, Derek, and Anna's projects from their web-based game and platforms. In today's forum, we'll be having 3 student presenters from our cluster who will be sharing with us their thesis projects. They are Anders Ang, April Zhu Weijie, and Lip Jiang. Before the sharing session starts, allow me to introduce our 3 guest speakers today. Dr. Patrick Jensen, Associate Professor at the Department of Architecture at National University of Singapore and the Director of the Design Automation Laboratory. Mr. Pan Yi-chen, Co-founder and Design Director of Produce Superstructure and the founder of Type Zero Architecture. Lastly, we'll have Mr. Vignesh Kaushik, the Regional Design Technology Director at Gensler. Our forum today is divided into 2 segments. In segment 1, we will have the guest speakers sharing with us their research and practice, followed by dialogue 1. And for segment 2, our students will be sharing their thesis projects, followed by the next dialogue session. Audiences streaming from YouTube, you are also welcome to post your questions in the chat box anytime during the forum, and we will bring them up to the floor. Without further ado, let us invite our first guest speaker, Dr. Patrick Jensen. He is an associate professor at the Department of Architecture at National University of Singapore and is the director of the Design Automation Laboratory. He is also the adjunct associate professor in automation in urban planning and design of the 3D Geoinformation Group Research Group at the Department of Urbanism, Faculty of Architecture and the Built Environment, TU Delft. He received his PhD from Hong Kong Polytechnic University, his Master of Science in Cognitive Science and Intelligent Computing from Westminster University, and his AA Diploma from the Architectural Association. Patrick conducts research into computational methods and tools for design exploration and optimization at the urban scale. His research focuses on democratizing urban data visualization, generative urban modeling, and urban density optimization. Today, he will be sharing with us about his research and his teaching of computational design today. Patrick, please.
Thank you very much. Thanks a lot for the great introduction. Okay, let me share my screen. And we go with this one. All right, so I have a few slides. So I think the aim is to keep this presentation short to 10 minutes. So I will do my best to do that. So today I'm going to talk about some research that we've completed very recently called Mobius Evolver. And I think that research fits into the theme of the discussion today and maybe prompts some interesting points in the discussion. So Mobius Evolver is a web application that allows you to evolve designs, do design optimization, and you basically perform the whole thing online in the cloud. You upload a bunch of scripts. In this case, they are Mobius scripts. I think the students all know about Mobius. Some other people who are watching this presentation may not know, but Mobius is a kind of 3D parametric modeling tool in the browser. So you upload your scripts and then you execute them in the cloud. And then this evolutionary process takes place in the cloud and allows you to optimize your designs. So this diagram here on the right is showing the sort of optimization loop where you generate, you evaluate, select, and then vary. And then that repeats itself. And through this kind of Darwinian process, the fittest designs survive, and they are used to generate more designs, and through that process, you get to a set of optimized designs. Now, the key thing about this slide is this little comment at the bottom is that it says it takes 3 minutes to generate and evolve 1,000 designs. Now, the reason it takes 3 minutes is that we're using this cloud computing platform by Amazon, AWS. And so AWS is really an amazing piece of infrastructure that opens up a set of a kind of hardware that previously was only accessible to, you know, the biggest companies in the world. Now this hardware is accessible to anyone. I mean, any person can just log on and create an account. And when you create an account, you actually get a lot of computing power for free. They give you a lot of free credits. And so actually every month for the rest of your life, you have access to a supercomputer and you can run a lot of computing jobs totally free of charge. So it's an amazing infrastructure that does democratize that whole ability to access advanced computing infrastructure. So what Mobius Evolver does is basically tries to make this infrastructure accessible to people who are not programmers, to designers and architects, in a way that allows them to evolve, use that infrastructure to evolve and optimize designs. And so here in this diagram, what it's showing is that the way that it works in Mobius Evolver is that you can upload different scripts at the same time. So in this example, we're just taking some very simple massing models where there's a podium and some kind of tower on top. And then there's one massing model where you've got a single slab and another one with 3 blocks, another with 2 blocks. You just throw them all up into this evolutionary process. And within a few minutes, it will evolve these designs and they will compete against one another. So we can see here the one tower one becomes extinct quite early on in the process. The 3 tower model becomes extinct at this point here, so that one also goes extinct a little bit later on. And the third one, the 2 tower model, survives all the way to the end, and we can see here the live designs are the ones here at the end. The little black lines are the live ones. So these diagrams here are actually the same diagram, just highlighting different members in the population. And the horizontal axis is the time, and the vertical axis is the fitness. So you can see as time progresses to each line in this graph represents one design. And so the height of the line represents the fitness of the design, and the color of the line represents which species it belongs to. So what I thought I could do, let me see how we're doing. Yeah, we've still got another 4 or 5 minutes. So what I will do is switch over and actually show you some of this in the browser. So all this technology is completely browser based, it's accessible and free. And so this interface that I'm showing here is Mobius Evolver. So there are a couple of Mobius models here that we created for, as an example, just for this massing here. Here's the one with 2 towers, and let me just move my zoom bar away. And here's the one with 3 towers, and each one of these has some parameters here on the left that allow you to change change the rotation and the heights of the towers and things like that. So the question for the evolutionary system is really which of these 2 solutions is better, but also for the particular solution, 2 towers and 3 towers, which set of parameters is better. And so we're evaluating the views down to the Singapore River, which are this is a kind of example in Bugis. So we're looking at the views coming towards the river. In this direction, we're looking at the solar radiation on the buildings, which is the sun is coming up in the morning from this direction and then going down in this direction. And we're looking at the unobstructed views out of the windows. So we're evaluating all that. We're evaluating every polygon on the facade with 3 different criteria, and we're doing all that 1,000 times in 3 minutes. So that is the power of cloud computing. So here we go back to Mobius Evolver. We can look at this run that I did previously. I'm not going to run it now because even at 3 minutes, it may take a bit long in a 10-minute presentation. So I'm just going to look at the results from my previous run. So here we can see the jagged line here is the number of generations. And as I hover over each one of these lines, I can see a little image pop up. I can click any of the lines here, and it will open up the design in the viewer here. So you can have a look at the design and look at a particular design from the population. And there's a number of other graphs. So the progress plot shows how the evolutionary process progressed over 10 generations. So here we can see at the beginning, the 2 species of design, this example here has 2 species. There's 2 towers and 3 towers. So here at the beginning, they are 50-50 in the population. And then gradually, the one which is 3 towers gets less and less because the performance of those designs is weaker. So gradually they get killed off in the population, and the 2 tower one performs better. So the 2 tower one at the end, generation number 10, only contains designs from the 2 tower script. And we can look at the parallel plots, which allows you to analyze a little bit more deeper about the parameters. So the live designs here are the ones which we can see here at the top with the different color here. And we can see that when you look at the live designs, the ones that have survived to the end, the number of floors of the podium and the relative height of the tower, those are two of the parameters. Those two parameters are very critical because nearly all the live designs have a very kind of narrow range for those parameters. This rotation one has actually got a very wide range, because you see the live designs are spread over quite a range there. And rotation two, they're kind of clustered, either very low value or very high value. So you start understanding what is the relationship between the parameters of your parametric model and the performance. The other design, this is the other species. They all died off in the end, but you can also have a look at those, and then the score plot. And so for each design, you can look at design and kind of explore it and upload it. We can go back here and only look at the, if we switch these off and just look at the live designs. When we scroll through this thing, you can start seeing there's a kind of pattern to all the live designs. The live designs always have one very tall tower at one end of the podium and either no tower, very short tower at the other end. So that appears to be the optimal kind of configuration. Seems to be one where you have the tall tower at that end of the podium. And then you can click on any of the live designs or any of the designs at all and load it into the viewer, and then see the kind of configuration of the optimal design. So the reason that this design is doing well is, from the solar radiation point of view, is that the tall tower on this side is actually creating a lot of shade, and the facade on this part is looking through that gap, and this part here is not obstructed, and you're still getting, two sides of the building are still getting a very good view of the river. So I think that covers my part of the presentation. I think I've already gone a couple of minutes over, so I will stop over there. So thank you very much. The end. Shall I stop sharing?
Yes, I have taken over the slides.
Yes, great.
Thank you, Patrick. That was a very informative discussion, and also a very informative talk on the Mobius program and the optimization process related to it, which provide us with new possibilities on design coding, optimization, and analysis. So next up, let's invite Mr. Pan Yichen for the next sharing. Mr. Pan Yichen is the co-founder and design director of Produce Workshop Limited and Superstructure SG, and the founder of Type Zero Architecture. These companies specialize in different fields: design, digital fabrication, and architecture, respectively, while working synergistically to enrich the built environment. Yichen has completed several internationally acclaimed and publicized projects, including Extra and Herman Miller Shop-in-Shop, Wild Rocket, and Kiki Sweets. Produce was recently awarded the 2019 IND Best of the Best Award for being a studio in the Indo-Pacific region that redefines and refocuses the significant role of architecture and design at present and into the future as well. Before this, he has accumulated more than 10 years of working experience in the field of architecture and academia, working with renowned international architecture firms such as ARUP, Advanced Geometry Unit, TP Bennett, Civil Architects, and UN Studio. He has also taught and ran workshops at the Architecture Association, National University of Singapore, and Singapore Polytechnic. Today, Yichen will be sharing with us on the topic of digital fabrication. Yichen, please.
Hi, hello everyone. Thank you
You
for
can
the kind
take over my
introduction. Yeah, I will start sharing. Right. So, okay, thank you again. So today I'm going to share on a little bit of my journey in digital fabrication. This domino by Le Corbusier happened more than 100 years ago. And at that time, it was the most technological advanced idea. He wanted to mass produce this domino in a factory, and then with minimal structural intervention, allow private owners to then customize their own interior design and even facade. So that this idea kind of died off. It didn't really happen. In the meantime, in the past 100 years, we have been building mostly in concrete and steel. We've depleted a lot of the resources, and now we are almost at the breaking point where if we don't do anything about it, we will not be able to, um, I wouldn't say stop, but slow down climate change. So also on the other hand, there's a severe lack of laborers. And at Asia, for example, is also facing an increase in urban population. So on one hand, there's a huge demand in building, and on the other hand, a complete lack of construction workers. And not to mention that all these materials are not recyclable and further damaging our environment. So I think we are at this stage of rethinking of the domino. And with the myriad of tools that we have now, computing and fabrication tools, we are able to perhaps create a new technological advancement in the realm of building. So my journey basically started from simply making stuff. I was teaching at that time in 2012, 2013. I thought like, why do we keep getting our students to do mock-ups and models in the workshop, but in practice, they would have almost no opportunity to do stuff like that. So I started my practice with a workshop on the ground floor, housing a CNC machine and a laser cutter, and my design studio on the second floor. Thereafter, we expanded on the workshop with a partnership with Emily and started Superstructure. And now we have a few CNC machines and hopefully looking at robotics in the near future. How we have actually organized our workflow had been quite haphazard. It was kind of guided by what projects we have. But over the course of about 8 years now, we have done quite a bit of computation to fabrication processes, ranging from material experimentation, component systematization, and assembly documentation. And this workflow, we are increasingly trying to streamline them a bit better, and even setting up a computational team within our practice. So as I said, we started simply by making. So I just like to share my journey in this through a series of projects that I've done since 2012. The first one was for a grid shell in Extra showroom for Herman Miller. We started with playing with plywood. This was simply hand cut. And the process of fabrication is simply just trying it out and testing it as a scaled model. And finally, we were then able to create this system of components and parts and start to modularize some of these elements, which then in this process, we created a new brick system. And we can't talk about digital fabrication without talking about assembly. So our very first attempt was very much very inefficient, simply designing the modules like bricks and laying them one after another in a particular sequence. This process taught us a lot, and further on in the next iteration for the Herman Miller Pavilion, we decided not to use so many different parts. There were 4,000 elements here. Yeah, so in the next iteration, we wanted to look at ways of shaping plywood without heat bending, but at the same time reducing the number of parts. So we started to cut into larger pieces, full panels of plywood. And then we use computer simulation to kind of simulate the elasticity of the plywood and to look at how they would bend when an operation is carried out. And finally, through this process, we created a parametric system where we can then define the dart angle based on the final bending of the plywood based on the dart angle. And so the fabrication process was simply using this minimal surface and then breaking them up into its 400 components. So in this case, the structure is more than twice the size of the first iteration in the previous Herman Miller store. But we have only like 400 components here. And there were, in terms of fabrication and assembly, it was quite simple. We did not need any skilled labor and it was pretty lightweight. In the end, the structure worked like a tensile membrane made of timber and simply was hung up onto minimal structures. Here you could see a hollow section forming the arch, which acts like a hanger that you will pull up a sail. So this was an important project and we learned a lot from material experimentation, optimization of the overall form, and finally fabricating it and also organizing the assembly. So since then, we were also involved in this exhibition at the National Design Center. So this was another minimal surface structure that utilizes plywood, but reinforced with laminate, HPL laminate. So likewise, we do one-to-one mock-up in the workshop. And in this case, as I said, we try to learn from past mistakes, and we did a lot more in the factory environment where we could have a safe place to make mistakes. And this was really a good attempt because we only took 3 days to assemble everything on site. So they were pre-assembled off-site in the workshop, and they come together really easily in a matter of 3 days. And the structure, because it was kind of optimized with a kind of gravitational model, it could carry quite a bit of weight, and we used very little material. So in order to create a volume like that, which is 10 meters wide and 5 meters tall, we only kind of used one pallet of material when we demolished it. It was just one pallet. Thereafter, we look at how we could segment organic forms into planarized components. So we started looking at this masonry shell, and we created a number of acoustic products. Right now, we are trying to make it into a product. At that time, it was a live project. So this was for an office. And we wanted to put panels of plywood together. In this case, we tried to simulate a finger joint, but with a bolt and nut to clamp it together so that the panels are in compression. And then the whole process was all digitally fabricated. They were pre-assembled into strips. And finally, when they go on site, it was going column by column, bolting these columns together, and naturally it forms the shape that was designed on the computer. So the whole process was a lot more streamlined now, and we started looking at ways in which we could expand this to other acoustic environments like a sound room. This became now we are doing the third iteration of acoustic shell. So this is for an office. So first of all, the process now is quite simple. We have written a system, a script, where we would first do a form finding. And this could be changed according to the size of the space. And then after that, we optimize it, we make it flat and create planar elements where the volume needs to be cut off. And then with the help of acoustician and our acoustic, the speaker supplier, we determine the positions of the acoustic panel and speakers. And finally, we start to modularize them and fabricate them. And this is a small mock-up. And finally, we redo the process again iteratively to create a one-to-one. So then we went on to compute for the fabrication. In this case, building up all the component parts, and also the two paths are all kind of weaved into the same system. And the kind of goal is to create like a one solid file where imagine the input of the space comes into this system, and then the output would be the fabricated panel. So it's almost like we are trying to create a 3D printer of sort. Yeah. And they come with their own serial number, so it would guide the assembly sequence as well. So this hollow bricks now comes together in a penthouse in Sentosa. So this is the back side where we would have infilled it with rock wool speakers. And the good thing about digital fabrication is that you can really create a one-to-one translation from whatever you have conceptualized. So this is the rendering and the build. It was just recently completed about 2 weeks ago. And finally, we are now gearing up to go larger scale into more building scale right now. So we started looking at reconstituted timber, primarily because mass engineered timber are, in Singapore, we still need to import them all the way from Europe. So it's not very sustainable. Instead, we should look at using regional plantation timber like rubber wood, and then compress them into really hard timber stock. So in one of our projects, we look at topological optimization where the column positions could be randomly placed, and then the waffle will kind of reorganize according to where the columns are. So this was a kind of very small test back in 2019, October. And then now we are looking at making them into standard components like floor plates, excuse me. Yeah, like floor panels and wall panels, which are load bearing. So this is for a two-way slab. This is the mold for pressing the reconstituted timber. And then subsequently, it's being pressed in this machine with 1,500 tons of weight. After that, heated. And what's removed from this? Yeah, is a kind of waffle component, which is very lightweight. 2 person can carry this. It spans 2.3 meters, and then about 150 mm thick. And we could use this cavity to run cables. Obviously, there are going to be acoustic issues, which we will then have acoustic sheets over and within, and acoustic foam within these crevices. And we were in the process of test loading this up to 1,000, 1.5 kilonewton. And now with this load and deflection, we are trying to optimize it a bit more. And looking at this as a system that could replace our precast concrete panels or precast floor slabs. In a sense, I think what we intend to do is to look at the entire built environment holistically. And finally, I think we, in this is the time that we, who are trained as architects, could reclaim the correct meaning of the the word architect, which is master builder, and transform the industry from construction, manual construction to fabrication, from on-site in situ construction to off-site, very clean factory environment type of fabrication. And with all these tools that are all combined now, we can be in full control of the whole building process and look at the whole building as a product, and reduce a lot of wastage. And I will encourage the graduating class to try adopting these technologies in their work when they get into the industry, because the architects need to lead this technological transformation instead of the the contractors or the fabricators, because the architect will be an important person to orchestrate all the systems together to form a holistic product. Okay, thank you very much.
Thank you, Yi-Chen. It was really amazing to see the comprehensive process of employing digital fabrication into architecture. And next up. Next up, let us invite our last guest speaker, Mr. Vignesh Kaushik. He draws upon more than 12 years of experience as an architect, researcher, and a design technology specialist to design and deliver several large-scale mixed-use projects across Southeast Asia. He currently heads design technology for Gensler in the APME and Greater China regions. He also serves on the board of the Computational BIM work group organized by the Government of Singapore to chart its roadmap for adoption of integrated digital delivery. His expertise is in developing scalable digital solutions with a deep understanding of functional, technical, and business needs. As a recognized thought leader, Vignesh has published several research papers in various technology conferences and is a frequent speaker at forums related to machine learning, design computing, and BIM. Vignesh also maintains a blog platform called Thank God It's Computational, with a mission to help accelerate the adoption of leading technologies among professionals in AEC companies. He truly believes in crafting incredible human experiences through digital transformation and storytelling. Today, he will be sharing with us Gensler's recent works and his ideas on how big firms leverage on technology. Vignesh, please.
Thank you. I'm so glad to be part of this forum here, sharing my thoughts on computational design and how we use this on large projects in companies like Gensler. But I'm just going to start my. Can I start showing my screen?
Yes, please go ahead.
All right. Are you able to see my screen?
Yep.
All right. Perfect. So today, what I wanted to discuss was kind of a two-part thing. One is a bit more philosophical, and then I want to show some examples of the philosophy towards or our approach towards design technology and computation in Gensler. Okay. So before we begin, I want to start with the word cognition. We want to understand the dynamics of human versus machine cognition, right? So we all know there are certain things about humans that are irreplaceable, right? Creativity, dexterity, ideation, handling ambiguous situation, critical thinking, empathy, sensory. All these are things that it's very hard for a machine to recreate. There are also certain parts of cognition where the machine is really good, right? About computation, logic, scalability, analysis, precision, coordination, memory. It's impartial. At least if your data is impartial, the machine is going to be impartial as well. So structure, everything, it's very structured. So these two cognition needs to come together in our tools, in our technologies to help us become better architects, okay? So this is the philosophy. This is a general philosophy that that almost any technologist would want. This is almost like Iron Man, right? You need Tony Stark, but you also need the suit. It's only when Tony Stark and the suit comes together, you get Iron Man. The suit on its own can only do certain things. Tony Stark on his own can only do certain things. So that's what we want to achieve. Now, on this continuum of human versus machine cognitive, there are many number of tools and technologies, and myself being a graduate from NUS, and an ardent fan and student of Dr. Patrick Johnson, who's my guru as well, and I'm so glad he's on this forum. We've explored this continuum a lot. We've explored things where certain things are a lot more intelligent, so it's autonomous intelligence. And then when I came to the industry, we can't leave so much of creativity out to a computer, so we have to take more control, so it becomes assisted intelligence. The fine part is how do you kind of get the middle, right? The sweet middle, where it is augmented intelligence, where the machine and the human are actually having a dialogue, basically, right? The machine helps the human in his thinking. The human leaves certain part of the whole thinking process to the machine because it relates to the cognitive function of the machine a lot more better than what the human can handle, right? Now, I'm going to show you a bunch of tools that Gensler has done in the realm of augmented intelligence. But before I jump there, I also want to show you a bit of the spectrum, right? So let's start with what does something like an autonomous intelligence look like, right? Wait a minute. Link is supposed to go. Okay. Let me jump in that PowerPoint. So this is a project that we did when I was with Patrick, working with Patrick as a researcher, right? This is for a developer who said he had a site, and then we had a certain conditions that we want to make sure that we are taking advantage of the site's views. We wanted to make sure that the units in the site, which the client, the developer wanted about 1,400 units on the site, right? So we wanted to make sure we are maximizing the value of the site and minimize certain things like the noise coming from the roads and all that, right? So the whole idea was, how do you get there without having to sit and design options, whereas it's all computationally generated. So we took a library of floor plans that typically sells well, and then an idea of how much from a marketing perspective, how many 1-bed or 2-bed you would need, and then we put a few algorithms together that can actually place units around the core, like 4 units per core, 6 units per core, or 8 units per core, and then we let the algorithm run. So this is a particle swarm algorithm. This was done on Houdini, actually. And then you see the gray boxes are your apartment blocks, your blue ones are your swimming pools, the green ones are the garden or the breakout spaces, right? And what the algorithm is trying to do is it's trying to fit these many blocks into a space, right? Into the space. And once it finds the perfect fit, it's going to stop, and that becomes a generated 3D option. So as I said, that's a swimming pool, that's the breakout garden. So once it becomes a generative 3D model, then you've got to take it through the 3 steps of the evolution of the evolutionary process that we had set up. The second step is to evaluate this 3D model for value analysis. So we have like a few analysis set up, like scenic view analysis. So every unit that looks into this canal is actually a premium unit. Every unit that avoids looking into each other's bedroom is a premium unit, so that's the value of privacy. And every unit from where you can get unobstructed view when you open the curtains in the living room becomes a premium unit as well. And units that can avoid the noise from the two expressways abutting the site is also a premium unit. So based on this, you actually put a dollar cost, a dollar value on this on each of those options, right? And then we let it run using a tool called Dexon that we had developed in the house. It's an evolutionary solver, something similar to what Patrick showed with the Mobius evolver, right? So what usually we will do is we let it run, go to sleep, come the next day morning, and then you've got several thousands of designs with you. So in this case, I think had about 20,000 designs generated in about 8 to 10 hours. And then this graph actually shows you what is the saleable value in millions of dollars. This is the window performance in terms of sustainability, which is like daylight performance and all that. And basically, you are looking at designs which are in this realm, very high in performance, very high in value as well. So, and then that's your Pareto line basically, and all the units along the Pareto line are usually investigated, right? Now, let's come back to the question of philosophy. Is this a designed option? Would you consider this a designed option? Actually, no, because this doesn't have a sense of place. This doesn't have the spatial quality that you need in a condominium design, right? So then why do we do this kind of stuff? Now, I would not even look at this as a designed option. This is just a visual representation of an Excel file. So this is very useful at a pre-feasibility stage for a huge developer who wants to understand the value of the land and how much he can develop, how much he can get in terms of millions of dollars that from that site, and is it even worth going and bidding for this site or not? You know, so these are studies where the human input here is to set up the algorithms, set up the parameters, and the entire design was generated by the machine here, right? So whatever intelligence that comes out of this is a very much autonomous intelligence, because the human did not have a role in it except to say, these are the things I want, now go ahead and find the solution for me, right? So this is an example of a design optioneering problem that took advantage of the autonomous solution, autonomous intelligence part, right? Now, I want to now jump into the example of assisted intelligence, right? This is a project which I did after I came to the industry. Right? This is where you are again automating certain things, but then the control is still with the designer on how much is being automated. So let me give you an overview of the project. This is a MRT station box. This is for the Thompson line. We had to design about 12 stations, all very typical underground stations, and then they are completely rule driven, right? Because LTA gives you literally a rule book of how you must do a station design, station box design, right? So we figured actually, you know what, this is such a rule driven design, we might as well automate the generation of this inside ArchiCAD, which is our BIM platform at that time, right? So what we did was to enable our designers to just control the generation of the BIM model from an Excel file, basically, right? So what they would do is just change the parameters of each of these different items on your model through the Excel file, and then the entire BIM model will be generated for them. So yeah, the designer what they would do is to just go and change the height, the width, and whatever the parameters of the escalators, the distance between them, a lot of these parameters, and then they would just run a script that we wrote. What the script does is it takes those parameters and creates a parametric nimble BIM model using Houdini and Grasshopper. And then it pushes that model into ArchiCAD to be a fully native BIM model, right? So this skeletal model, we are using Houdini um, as the parametric engine to develop this because it was quite complex to kind of get this done. So we use that. But what Houdini produces is just a skeletal model, right? And then this skeletal model is then automatically imported into Rhino and Grasshopper. And as soon as this is imported in, ArchiCAD is looking for data to come in, right? It's constantly looking for data to come in. And as soon as it recognizes that Grasshopper has some data and geometry, it converts that into a BIM model, right? And this is native BIM model. This is not a mesh, or this is not uneditable stuff. This is actual native BIM model that has escalators and everything's floor slabs and walls and all of this done, right? So if you look at this, this is automation, yes, but the process is still driven by the human because the humans decides exactly what each of those parameters should be and stuff like that, right? So now I've shown you two examples of the spectrum, which are kind of one at more towards machine intelligence, one more towards human intelligence. And as I said, the part where we are more interested in is the augmented intelligence part. So that being the philosophy, what we have done in Gensler is to create a platform called Nform, right? Now, Nform is a platform that allows us designers to actually create some of this intelligence as a tool. So we have few tools created for them. So GBlocks is a tool for architects, for architecture and urban design projects. GStacko and GFloors are tools for interior designers. And GMP is actually is a library of materials that all of these tools can use to create amazing renderings, basically. So I know we're running short of time, so I'm just going to show you how GBlocks works, maybe, right? And then maybe on another occasion, I'll walk you through the other two. So with GBlocks, this was a tool that we did about a year back. This is a plugin to Rhino and Grasshopper. And the way the tool works is it provides data insights to the designer while we are working on the BIM model, right? While we are working on the Rhino model. So this is a data-rich conceptual platform wherein I can actually program on the fly. I will know the financial impact of the design. I can get rapid decision. I can make rapid decision based on live data. We will be able to know parking goals. We are able to calculate cost versus yield and how much the budget is. All this right from a dashboard that comes in front of you while you are designing it, right? So typically what would happen is designers would design something, they'll stop designing it, they will have to go to Excel to do all kinds of different calculations on GFA, site area, total cost, and yield, on parking numbers and all that. And it was actually a very disruptive workflow. While now what we are able to do is to make sure that there is no disruption to design at all. And all these metrics are shown to the designers while we are designing. So this is a YouTube video. You can go search for GBlocks and you'll be able to find this video. So one of the first things we do is we set the envelope for that particular site. So the minute we go outside that envelope, the tool is going to say that, hey, you are breaking the local compliance code. So all the designs that we are doing already is compliant. There is no need to run a compliance check later on according to standards or the local building codes, because this is already done while we are designing, right? And we are able to create all kinds of different programs, assign target areas, and then you can watch whether are you able to hit the target areas or not. The ratio between these different programs is also shown. You can create any kind of parking, underground, overground, on the surface, and all these numbers are automatically calculated, right? And of course, you are able to rapidly make design changes and create design options, and then you're able to compare and contrast the different design at scale. And of course, financials. So while you're doing it, you're also able to have financial data, adjustable inputs. So this is what I meant, where the data and insights that the machine is able to provide while you're designing it is very useful to the designer, because he still retains the design control of what is being drawn on screen, but he leans onto the machine to give him insights on data, right? So this is almost a standard tool at this point for us for all our architecture projects. We have used it on many projects, small, big, it doesn't matter. And this is something that our clients absolutely love, because in fact, we involve them in the design process using this as well. So typically in a client conversation, the client would say, hey, how about we do this, right? And about a year back, you would be like, oh, okay, let me get back to you on this. Now, what we do is we say, okay, let's check it out right away. What does that mean? So that's the difference basically for us, right? Is to be able to bring live data and live feedback to the client on the client call without having to keep going back, because the data is just there in front of you. So these are some projects in China, some projects in Singapore, some projects in the US, where we have used it in many different ways to advise our clients on what's the best mix of retail versus residential, where can you get the best yield. So yeah. So, and then of course, we then combine this with simulative technologies for running environmental simulations, right? Like sunlight hour analysis, like daylight analysis, wind analysis, solar irradiance, understanding PV output, and then this is then we are using a process by which our design exploration is in Rhino and our design deliverables are on Revit, right? So the entire interoperability is taken care of through automated tools on our end. So the designer is not redrawing anything in BIM at all. He just takes the Rhino model and then it auto converts into a BIM model using some custom tools we have built. So it is a very much performance-driven design method, but it is also a process where the design control is still with human. All right. Okay. So I think, do I have more time or is that it?
I think time is running short, so we'll have to move on. And we can mention more things during the discussion in a later stage. Yeah.
All right. So then that's it for me. I just wanted to show you one tool. Then we'll see if we have more time for the others or maybe a different forum for this. Yeah. Thank you.
Thank you a lot, Vignesh. So now, thank you for all our guest speakers. And now we have come to our first short dialogue and Q&A session. We will also welcome our student presenters to join us in the dialogue for discussion. For audiences streaming from YouTube, you are welcome to post your questions in the chat box, and we will try to bring them to the dialogue. And more questions will be answered at the second dialogue session later as well. So this one, we will keep it short as possible. So to start with the dialogue, I will pose a first question for all our guest speakers. Could you share with us with your ideas on the role of architect in a world where technological tools are augmenting or even slowly replacing the designer's role. Some examples being the new AI technologies as shared by our speakers, and also machine learning and digital fabrications.
All right. I know we all share different kind of tools and technologies, as you mentioned, AI, machine learning, all this. But there is one very powerful tool that I think we all must learn. We are constantly learning on a daily basis as well. And that very powerful tool is empathy, right? As architects, sometimes these tools can remove you from the actual um, the final user who's going to use the space, right? Um, and your focus can kind of get into very simple things like, oh, how do I move this geometry from this tool to another tool, right? So I think empathy is very, very important in all these cases. And then when you start to understand the space and empathize with what is being asked on the design brief, the tools and technologies will automatically be the leading you to that, and not that you want to use a tool or technology for the sake of it, but you know exactly why you are using it. And I think by learning empathy and by learning to understand the design brief, is very critical in my opinion, to choose the right technology for that for that project.
Thank you, Vignesh. Any sharings from Patrick or Yi-Chen?
Yi-Chen, you want to go first, or shall I?
Okay. Yeah, the question of what the role of the architect is in a world where machine seems to be taking over is that I think it's more of a question whether we could build a system where what Vignesh says, that empathy can still be involved, in the sense that machine will make everything so smooth. You can set up your parameters and you can set up your conditions of generating the entire city, but we know that cities only become more interesting when there are exceptions. Like we like the accidents in the city. For example, like Times Square would be something that is deviating from a grid, or like the Diagonal in Barcelona, which makes a lot of unusual blocks. So how can machine learning or even computational systems help to create enough gaps where exceptions can still happen? I think that's very important now, because otherwise there's no role, not really a role for the architect. And human behaviors and human endeavors are, I would say, not so predictable. And the human spirit cannot be just simply be a result of computation. Yeah.
Yeah, so maybe I tackle it from a different point of view. So I think one of the things is that the role of the architect is very much also to do with competition between architects. So I think the machine as a kind of device is going to propel certain architects into a different mode of working, which offers better products at a cheaper price. And which basically means it all comes down to scalability. So, if you've got a set of tools in your office and you can do 10 times the jobs that the guy in the next office can do, right? 10 times as many jobs, then you're going to be raking in the money, right? You are going to be cutting the price and raking in the money, and the other guy's just going to be out of the game, right? And so I think it's not machine versus human. It's really this thing is coming, and everybody's struggling to figure out exactly, what's I mean, like Vignesh was saying, this middle ground where the architect is still very much in control of the decision making, but they're kind of empowered with these tools. I think that's definitely the way to go. But really, the role of the architect depends on what the other architect is doing, right? And maybe in the Singapore context, what offices in China are doing, or what they're coming in and they're undercutting prices. I mean, so Vignesh's office is the largest architectural practice in the world, and so they have huge scalability advantages, right? So when somebody has an office with 5 people in it, how do you compete? But in a sense, that Amazon technology that I was talking about does level the playing field a bit, because Vignesh's office, which is the biggest in the world, versus the small office, have the same technology, same hardware. There's no difference in playing field at that point. So really, it is the amount of investment and time and stuff that you can put in. And so I think small offices have to carve out their niche. I think Yicheng's projects that he was showing are really amazing. And obviously, that is a very specific niche where, another office may not have the experience in that niche, and so they can't compete with that. But so I think really this whole relationship with the computer and the architect is to do with ruthless competition at the global scale between different practices, and not only architects, but also people trying to cut out the architects. I mean, there's lots of companies now trying to say, we can design a building without an architect. What do you need those architects for? They're just a pain. And contractors who are taking over the architect's role, and developers. And so, it's getting more and more ruthless, and it's accelerating at a faster rate. And the old model of architecture, where you sit down and a client walks through the door and you do a one-off project, becomes very, very difficult, because you can't compete. You can't compete. If you have to reinvent everything every time, you just can't compete. So you have to have a kind of expertise that you take from one project to the next, and that it becomes a very kind of sellable skill that somebody else can't just come in and say, I can do it for half the price.
Thank you, Patrick. We have a few questions coming from the audience. So the first question is for Vignesh. Do you find so the question is from Kiki Yap. She's asking, do you find it difficult communicating optimization ideas to the clients in the real practices? And how do you repackage and deliver your ideas to them?
That's a good question. So whenever we are having these kind of client narratives, right, the focus is on the outcome and not the output. There are two different things. Okay, the outcome is a feasibility study for the client, right? The client, when there are maybe 1 or 2 people on the client who's interested to know what the technology behind what we did, right? So we will probably get to that when they ask for it. Otherwise, the technology is just in the background. It's your secret sauce in the way you achieve what you want to achieve. It's a feasibility study, right? The feasibility study can be done by one person drawing up maybe 3 options by hand, or using an optimization process where 10,000 designs are drawn and you are showing a few of what you think are the best out of the 10,000, right? So the narrative really depends upon what is the client need and what is the outcome you are after, right? And we have not had any problems with that, because the clients actually love all this. Like Patrick mentioned, this is our differentiator. Now, everyone on this call must understand, as practitioners, what is your differentiator, okay? And this differentiator is very important when we go for client pitches, because they would want to see what is, for example, Gensler bringing to the table that another competing architect is not able to, right? And how does that thing that we bring to the table aligns with what the client wants to achieve for himself, right? So this is very important in that sense. It's like, how do you align your priorities to the client's priorities? How do you align your technologies to the ultimate outcome that the client is expecting? So it is not so much about the nitty-gritties of the tool, but it is about the outcome.
Thank you, Vignesh, for your sharing. Given the time limit, we will end this dialogue session first, and then we can share more on other questions in the dialogue 2 later. So now, let us move on first to the next segment, where the student presenters will share about their thesis projects. We will have our Q&A and dialogue session later again for our guest speakers and student presentations after this segment. Let us invite our first student speaker, Anders An, to share about his work. His work titled Topological Space for the Masses. You can take over the screen now.
Yep, give me a moment. Okay, and is it working?
Yep.
Okay, hang on, let me just go to full screen on this. It's not sure. All right, so hi, I'm Anders, and this is my thesis. Basically, on a very basic level, it looks at how we use computational tools and techniques in architecture. Right, and it all started with a comment from President Scott Bowen, right, about the use of parametric tools in a particular practice. Right, that has mostly been applied to the skin layer of architecture, while the interior remains the same. So as we look at these two examples, Morpheus Hotel and Legal House, these buildings are 50 years apart and built in very, very different ways. If we strip away the skin of the first one and the second one, we realize that, hey, actually, in the inside, we see the old model of absolute repetition. It's just a domino house on the inside, right? The interior has not changed at all, right? We look at another example, 1000 Museum. Again, you strip away the skin on the inside. Well, the floor plates are maybe a little differently shaped, but then they're all just repeated again. Right. And what this reveals is that even as we use new computational tools, right, how we think, how we design, and how we inhabit architecture, right, does not seem to have seen the radical shift at all. We've been using computers primarily as drawing tools. Like in Frank Gehry, he sketches out this thing and then he builds it in a computer, right? But it's always almost like for an optical style, right? A pavilion is still a pavilion, a building is still a building, a tower is still the same domino structure on the inside. Everything else is pretty traditional, right? And these users do not quite represent the true benefits of computational tools. One of the ways this affects us, everyday people, is in mass housing, right? Because of this lack of radical shift, right? It carries over and can be seen in the way we design our mass housing today. And if you see the plans of our HDB flats, they have not really changed, right? From the 1960s until 2000s, right? Even worse, if you look at all these HDB flats, right? They're just copies of the same unit repeated over and over again. And this has been the way that we design mass housing, even though we have switched from plain paper drafting, right, to using computers in our workflows. So the question is, how can we move beyond that? How can we move beyond just using parametric design for skins, for pavilions, right, for energy simulations? And how can we move beyond that old model, right, the old modernist Fordist model of absolute repetition where every unit is the same? Right, it's a mass-produced kind of space. How can we take computational tools to the next level beyond this? Right. So I've been looking into some ways that we can do that in terms of breaking away from old modernist spatial logics. Right. How we can move away from certain ideas of architecture where when we start the building, we start with a tabula rasa. Right. We wipe the slate clean. Right. Start with a flat ground. Can we move away from that and use new data like from satellites, from terrain analysis, from 3D modeling to simulate, right, our terrain before we start working on it, right? And how can we use tools of the computer, right, discrete objects, and then repeating them throughout in different ways to come up with very complex but still buildable architecture, right? Also looking at certain philosophies, right, and certain concepts that have been brought up in the past, such as Bernard Cash objectile, where instead of designing a singular object each time, you're designing a set of relations, right? And how these relations can allow you to create variants of the same design over time, right? And also looking at how other democratic inhabitation strategies can occur, right? And how platforms can come in to play with this to allow people to have a say in the way they design, right? So as a demonstration of how we can use all these computational tools, I'm focusing on the side of Tengah, right? So basically what I'm trying to do is I'm going to take VOA's master plan for Tengah and develop an alternative, right, that uses computational tools to analyze and then propose architecture on the site, right? So allow me to share a small video with you. This video will be is a workflow of how I've used these computational tools, right? And in a way, they sort of demonstrate how we can use computational tools to consider certain phenomena, right? Things like the terrain from satellite data, things like how does water flow in the site. So over here, we're doing a simulation on the water flow and figuring out where we can draw rivers throughout the site, right? Figuring out how we can connect the existing connections that run through the sites. We can figure out what are the age conditions, right? We can do network analysis. Where are the areas on the terrain that we can inhabit, right? What are the age conditions? Are we going to separate the site into parcels so that we don't have a massive block, but we're separating it into smaller blocks with perforations here and there for services, for networks, for lift costs, right? And mapping that into a mesh that allows us to create a grid of sorts, right? That eventually transforms into the architectural form. So what you see here is just me creating grids of space, right? They are eventually extruded into cubes, right? They're stacked together, right, to form this architectural space that is in 3 dimensions, right? So this is just a few decisions that I make along the way, like, okay, maybe let's connect top of the building so that, we can have some sky bridges here and there. So it's running through the same process again, considering all the age conditions, all the solar conditions, right? And generating it for you, right? And then identify where structure goes, and also doing some sort of a spatial analysis to understand where are the denser areas, where's the areas with the highest height, right? And then using that data to scatter my cores, right? Where are the cores where lift cores can go, stair cores can go? How do we connect each cores using shortest path networks, right? So that they're very, very efficient, right? And how can we locate to say, okay, which are the areas where I need a bigger core, which are the areas I need smaller cores? And then at the end of the day, this is what we receive. And then we can not only just do one variant of this, but we can create a few variants based on different kinds of requirements. So perhaps we want to have more space on networks, we can create a variant for that. We want to have more space on edges, we can create a variant for that as well, right? So in this example, this is a variant that goes across the rivers instead of avoiding them entirely. So at the end of the day, we see that this thing that I've created is very complex. So let me just go back to the slides again. Right, so it looks very complex, but actually it is made up of very, very simple modular structure. So because each volume is a cube in itself, right? We could bound each volume by having just some modular parts, right? Slabs, waffle beams, columns and beams, right? And then combine them to form the structures, right? As well as a modular system for the service cost, right? As a way to also construct this, to construct the rest of the architecture later on, right? So what you saw earlier on was also very, very complex, and you will not expect someone to have, let's say, someone to have the model in SketchUp and then try to draw residences on every single one. It will take them forever, right? So what we could do also is to provide some sort of a support platform, a digital support platform for people to come in, be it the developers, be it the architects, or be it the users to come in to analyze, right, how this space works. So things like how the rain flows across the site, how wind flows across the site, right? What's the amount of solar radiation in space gets, right? And right, we can combine all these spatial qualities to figure out, okay, where are the spaces that are great for public spaces? Where are the areas that are great for office spaces? And we can use it to map spaces that are great for, different kinds of programs. And then later on, we can come in to say, okay, this is the area where we should have commercial, this is the area where we should have public spaces. So it aids in that process of deciding where things can go. Right. On top of that, perhaps we could also open up this platform, right, to the users in a way that is some sort of like a Sims tree but multiplayer, right, where we receive this empty structure and then people come into drawing, okay, where do they want the units to be? So in this example, what you're seeing is you're just seeing sort of like the end result of people drawing in where they want their units to be. And you realize later on that all these units are very different. Right? You can come in to use this platform as well to negotiate with your neighbors. Let's say perhaps these two units share the same slab, right? Someone uses it as a terrace, someone uses it as a roof, and perhaps they can share the cost of it as well. Right? And you can use the same system to understand, okay, what happens if you want to change the space over time? Right? So this is the initial stage, and then after modifications. Right? So what happens in the modifications? What are the negotiations that need to happen? Right? So for example, in this guy over here, he wants to expand his unit, right? And then he creates this extra slab that can be shared by the neighbor, and then they can do some sort of negotiation to understand, okay, what needs to go on with the cost sharing issues, right? And then you also flag out issues with things like the fire code, right, which are all considered in the model, right? Issues like how do you run all the services that is needed, and how do you reroute them later on, right? So at the end of the day, this whole model allows you to create this whole variety of spaces automatically, right? And the platform also allows them to change, right? The users themselves to have a say in how these designs are changed over time, right? And the whole workflow kind of works kind of like this, right? What we have designed earlier, what we saw earlier is just me making the decisions to design an algorithm that comes up with the whole skeleton of spaces, and then people come in to fill in the space. Right. And then after filling the space, after the contractor builds it, after they modify it a few times, we take the usage patterns, right? How do they use the space? What modifications do they make to the space, right? What are the shortfalls, right? And then we feed it back into the design process, right? In a way that we take this example, this is variant 1.8, where we have, just a structure like that. And then we realize that perhaps, people want to build it over the river, right? We can take that data, feed it back into the design process, right? The algorithm, change the algorithm later, and then have it to consider what happens if you want to include, right, building over the water bodies, right? So at the end of the day, this is just a way I demonstrate how we can use computational tools and ideas in new ways, right? New processes, right? And to create an architecture that creates a variety of spaces, right? And are able to adapt to different conditions. And a process also that helps users to be part of the design and of the redesign of their spaces over time. Yeah, and this is what I have. Thank you.
Thank you, and thus now we will move on to our second student speaker, April Zhu Weijie, to share about her work titled Reverse. You can take over the screen directly.
Hi. Can everyone hear me?
Yes.
Yep.
Yeah. So my project is going to be quite different from all the projects that's been shared just now. So instead of my project is instead of optimizing the way that architects design architecture, it's more like a critical and theoretical discussion of how technology is going to restructure our society in the future and bring about a series of social problems. So it's going to be a bit different. So I'll start my presentation. Sorry.
Hi, I am your AI narrator. Today, I am going to tell you a story about hope and aspiration in a community of useless. The core question that inspired this story is that when artificial intelligence replaces our job, what will we become? And how should we face the new reality where we have little to contribute to society? This might seem very far away, but in China, automation and AI has already started to displace the less privileged. A class of useless people, which is coined by the scholar Yuval Harari in the book Homo Deus, is emerging on the streets of Shenzhen. They are called Sanherdashen, which means Sanher gods. The Sanher gods were originally aspiring migrant workers from the countryside who came to Shenzhen aspiring to live a better life. However, most of them could not find a stable job and became Sanher gods. Each morning, at 5 a.m., they would be waiting outside the talent market, fighting for the limited day job slots. Those who manage to get a day job will be sent to factories and construction sites that need extra manpower to pick up rubbish or do other tasks no one wants to do. When they can't find a day job, they will sleep on the street in Sonor and survive on offerings from others. Some of them starve to death or even go crazy. The community has a culture of work one day so that you can play for 3 days. They call themselves gods, as they have transcended the desire for climbing up the social ladder, living a carefree life without goals nor aspirations. But the harsh truth is that since 2018, factories such as Foxconn plans to replace 80% of workers with robots in the next decade. In near future, there will be more Sonor gods and less jobs. Many Sonor gods have accepted such life. Song Chun Jiang, for instance, sold his identity card on the black market for urgent cash. Without his identity, he could never take up any permanent jobs ever again. He is also in heavy debt from internet loans. There is no way he can ever return the money. Yuval Harari worries that the problem of the useless class is not just the loss of jobs or income, but more of a sense of despair when you are locked out of the only perceived way of a meaningful life, which in many people's case, is about earning money, gaining status, etc. You will lose your hope in life and find it harder and harder to get up in the morning to do anything. So these Sonor gods will only find work when they are hungry and eat the cheapest noodles. They stay in dirty clustered internet cafes and waste their days away in online gaming. The scary fact is that with the AI revolution further widening the social gap, we can even expect those originally hard-working folks getting replaced by AI. So this is a map of Shenzhen, and the Sonor area is in the heart of the electronic factory district, Longhua. The Sonor talent market is highlighted yellow here. It is surrounded by urban villages populated by Sonor gods. In the future, even more workers will be displaced and they will cluster in these slum-like urban villages. This will become a huge social problem that needs to be addressed. So that is the problem I'm investigating in this project, and I'd like to create a community for the useless class where they could have a new set of aspirations in life so that they can still live a purposeful life even after they are replaced by AI. So I'm imagining a new community built on the grounds of the Son talent market, where every useless class can now have a new start to build his future. Since they are unable to progress in life by earning money, we can introduce another form of progression, which is in terms of social credit scores through contribution to the community. This system is inspired by the government's social credit system and the computer games where they are spent all their time in. The social credit system we have is very much like the quest and reward system in role-playing games. As players complete quests, they gain experience, level up, unlock new spaces and receive items to play the game better. Their ultimate reward for finishing the game is to upload their consciousness into the digital world where they could be whoever they want in a virtual heaven. The path to the digital heaven, which is the top of the tower, takes many decades. Most of the community, including the tower, are designed for the residents to spend most of their days meaningfully. I will now bring you into the tower, which is the symbol of hope in this community. The tower houses the key industry of the community, which is e-waste recycling. In fact, right now 70% of the e-waste in the entire world end up in China, and the majority are dumped around smaller cities near Shenzhen. So the tower is made up of 6 sections, and each section is designed to house specific activities that correspond to the current social level of the resident. As you accumulate social credit score, higher levels will be opened up to you, so you'll have more choice on what you want to do. And when you reach level 100, you will be able to go to the top where the digital heaven awaits. The very first space that is open to the newcomers is the e-waste dump, which is also the scavenging arena. Every morning, trucks carrying e-wastes will dump them to the ground. Scavengers take up quests in this area to pick out the valuable e-waste from the dumping ground. The quest in this section is to collect many valuable e-wastes as possible. And just like in computer games, the residents can choose different difficulties where they will receive higher rewards for the harder quests. For example, if you are strong and fast, you can compete in the Battle Royale mode where you earn additional rewards for outwinning other competitors. Residents can redeem their rewards to exchange for services like haircut or food. But most importantly, they get equipments that will make their effort easier. In this case, these are various gears that help in scavenging. The second space open to residents is a sorting arena. The second space open to residents. The scavenged e-wastes are moved upwards in a central pipe. Sorters have to classify the e-waste by running around and throwing them into their specific chutes. All the sorted e-waste will go up the peripheral suction pipes to the next space, which is the dismantling arena. The third space opening to residents is the dismantling arena. For instance, monitors need to be dismantled into CRT, circuit board, cables etc. In this area, there are mobile capsules on the outlets of the sorted waste pipes. The capsules rise from the bottom to the top. In the quest mode, residents work in the capsules to dismantle the e-waste within a given time. The more experienced ones can also choose to compete in team races, where each capsule is a team, and the cumulative progress of dismantling determines the speed of the capsule rising. Residents gradually receive various equipment which makes the dismantling process easier. The next space is the heavy machinery zone, where the dismantled parts are melted and processed into coarse mixtures of materials. The zone is separated into 4 identical sections. Players work in teams to adjust the different settings of the machines on the fly to adapt to the incoming raw materials. For example, they need to adjust temperature or pressure settings to create a ferrous metal mix, or a plastic mix as the input from the below zone changes. The 4 teams can compete against each other and the best team could win a bonus reward. The next space is the makerspace, which is a mixture of refineries, labs and classrooms. This zone is dynamic and full of places to explore. In this space, the raw materials separated by the heavy machinery below are converted into valuable materials such as precious metals like gold and platinum. The refineries and labs are blended together with learning, working and leisure spaces. The next space. Eventually, one will be offered the final reward of the community, which is to upload his consciousness to the digital world where he can be one with the AI. Along the progression, residents could come to the altar to witness the formation of their digital avatar. Underneath the altar, there is a museum open to the rest of the residents where they can interact with the uploaded beings, which continues to motivate them. The uploading ceremony is a monthly grand event held in the altar, where eligible residents with higher scores will be invited to attend. In the realm of immortality, the altar and theater are surrounded by data pods which houses the digitized consciousness of the uploaded residents. In the middle is the supercomputer, which is also the AI which manages the social credit system, governs the community, and maintains the digital heaven. The tower acts as a symbol of the progression system in the community. One is initially replaced by AI and cast out into this neighborhood. He starts his life afresh by taking up quests posted by the AI. After accumulating enough experience and knowledge, he is able to work with the AI to create value for the community. Eventually, he becomes recognized for his service and is invited to join the virtual world maintained by AI. This progression contrasts the current condition of the workers in Shenzhen, where they are only exploited for their youth. Once they cease to be competitive, they will be abandoned like e-waste. Whereas here, like how e-wastes are slowly turned into gold, there is a definite path to advance upwards. For each higher level you reach, you will become more valuable for the community. Eventually, you become immortalized as a testament for all. So that is the new social progression system and aspiration that the tower wants to enable in the community. And this new social paradigm will also affect the surrounding villages. With the raw materials extracted from the makerspace, the current urban villages can be slowly transformed by its residents in a bottom-up manner. As you can see from the master plan, we want to inject a new circulation that connects the tower to the urban villages. The Sky Boulevard facilitates pedestrian circulation as well as the transportation of essential materials. The bottom-up urban transformation is enabled by regenerative nodes that we insert into the current fabric. Each of the nodes is actually a mini 3D building factory. Firstly, The factory receives raw materials such as plastic, metal and glass from the makerspace and creates PPVC modules. Then, the modules are then hoisted upwards to the crane, which helps to install completed modules onto the top of the existing residential blocks. The node also serves as a platform where residents can build civic spaces from the schematics designed by the inventors in the makerspace. Now, I will bring you into the urban village to see how the urban fabric is gradually transformed. The transformative process can be separated in 3 stages. In the first stage, the nodes are added and linked to the factory tower with skywalk. These surveillance poles are also added to reinforce the current buildings, to support the placement of additional roof structures. At stage 1, the residents are still mostly staying in the current condition, but already have the social credit system in place. Gradually, as the residents in the community level up and get more rewards, they can pool their points together to improve the community by growing the civic spaces up to their preference. At stage 2, residents begin to use the regenerative node to build better housing on the existing structures of the urban village. Eventually, as the engineers and inventors in the makerspace create new schematics, each of the neighborhoods can grow in very different directions. So one community might like to be rich in night activities and another might wish to go green with urban farming. The I-governed benevolent dictatorial society is hailed as a communist utopia. So when looking at the scheme as a whole, this is a community where the useless class rejected by the AI revolution could gain a new life and a new purpose. Unlike the constantly changing world where you really don't know what you can do in life, this community assures the useless class with a definite goal in life, which is the promise of digital immortality. To ensure they are motivated to finish the long race to a new life, we use a game-like progression system where the residents can have constant feedback and rewards to keep them motivated. While the progression and quest system within the tower is governed by AI. Back in the villages, residents have the freedom to shape their living spaces and amenities, which will give them a small window for creativity and foster a strong sense of belonging to the community.
So that is all. Thank you.
Thank you, April, for bringing us into a completely new future imaginative world. So now let's move on to our final student speaker, Li Jiang, to share about his work titled Deconstruction and Reconstruction. Li, please.
Hi, so I'm gonna go through this as fast as possible due to time. But my project is titled Deconstruction Reconstruction, and I'm looking at architecture through the lens of structural optimization. So basically, construction accounts for about 39% of total embodied carbon in the world, and structure is actually about 1/3 of that, so about 11% of all the sort of like embodied carbon in the world. And so therefore, if we utilize less material for our structure, we actually have a better ecological footprint for building society. So basically, I'm looking at 2 kinds of structures. So one is shells and one is frames. And what I did in my methodology was basically to deconstruct architecture into its component parts, into floor, wall, ceilings, for example. And I look at these parts and I see which ones I can apply my 3 processes onto. So these 3 processes are topological optimization using evolutionary solvers. So this is stuff that sort of reduces material and adds material at the same time. Second is stress line optimization, and third is 3D graphic statics. In my second part, I sort of put them back together, reconstructed it, tried to see how multi-story aggregations will work, and I eventually have 4 architectures that I will share with you today, sort of like examples for how they can be utilized. A question that I get is basically its relationship to engineering. How is this project might different from trying to be an engineer? So the thing is, I'm interested in how the space is utilized, the topology of force transfers, but not really the calculation, and somewhat I'm also interested in the material sciences. So these are the 4 architectures: aggregation, 3D graphic statics, stress line analysis, and macro and micro BISO. So these are the processes I utilized. So first of all, for the discrete aggregations, I created a factory, and these are made from individual components that have gone through topological optimization. How this works is that you can see the image on the left. There's a loading condition at the top and a support condition at the bottom. And what it does, it tells me where I need to have material and where is material most important and where I can reduce material. So for example, from this, I'm able to generate my discrete elements, so to construct these as meshes and then utilize them as columns and floors and walls. And then what actually happens here is that I can pull them together into making this sort of factory floor space, put in office floors in the mezzanines, put in spaces for delivery trucks. And the main space is, of course, a production floor that can self-replicate. So the space is designed to allow for the self-replication of more of these discrete elements to create something like a RepRap printer, which is a self-replicating 3D printer. So this is how it looks like from the inside, view over to the production floor and from the office, the main alleyway where the trucks can drive. And the ramps themselves are also optimized. So there's utilizing MikeCS Amoeba solver, which allows me to do more complex forms using the same sort of idea. So this sort of reduces materials and adds material where it is required. Hopefully this isn't too laggy. Okay, and this is what the ramp looks like. And next, I also explored 3D graphic statics, which is sort of devised by Philip Bloch. And what it is essentially like a physics free body diagram, but instead of doing it in 2D, you have it in 3D. So form diagrams, force diagrams are sort of represented by polyhedras. So this polyhedron means that there are forces coming in this way. So for example, in this tetrahedron, there's a force coming in and from each of the face, and each of the face represents, this area of each of the face represents a sort of magnitude of the force. And then these lines are the eventual form that will react. So it is trying to react to forces coming in from these directions. So with each subdivision, you get a more complex topology inside and a more complex branching and sort of transfer of forces. So I explored different ways that I could utilize this to create form. So as an architect, what we do is that we will study these tools and think about how we can utilize them to carve out spaces. So I devised a sort of a table of methods, and I eventually use them to create this, which sort of takes in forces from each of the faces, and then it reacts to the forces to create and carve out these eventual spaces. So this, and I devised it as a gallery space that sits across the production floors that people could look into. The form is quite complex, but it all represents efficient transfer of forces within its structure. So you can have a gallery floor that sort of sits within it, section through the space. And this is the view of the production areas from the viewing areas. And the view from underneath the space, a white canopy of a cafe. So you can think about how different spaces become utilized. Thirdly, I also utilize stress line analysis. So this is, of course, to create a high-speed rail. This is, of course, influenced by Pierre-Louis Guinerby, his famous Getty Wool factory, where he extracted the isostatic stress lines from any shell structure. So this system is good because you can utilize Millipede or Karamba solvers to sort of extract the principal stress lines from any sort of 2.5D shell structure. And what I did was actually devise the manner of utilizing these stress lines to turn them into a utilizable geometry. So this sort of large span is sort of optimized to sort of bring forces down towards each of its 4 corners. A view of how the railway is can be utilized from the inside. And finally, I also utilize BISO in my own methods, which is what I call macro to micro BISO. So one flaw about this is I cannot have very detailed optimizations because I lack computing power, but I can probably solve that with Patrick's use of AWS, right? So what I do is I envision this as a parasitic space that sits in between these structural frames, like it's a new house in between 2 party walls with a structure like this. And I'm trying to latch these spaces onto the structure. So the architect can define where the spaces are, and then how we do this is that we sort of define the large domain and then see where the macro topology optimization. So you can see that forces might be running down this way and this way and this way. And then this is my first study. And afterwards, I break it down into my smaller spaces and then optimize each individual space, utilizing lessons that I've learned from the larger optimization. So this helps me to solve the problem of resolution which I had. So these are the individual spaces being optimized. And then all together, this is what it looks like. Sorry, I realize it might look laggy on your screen, so I'll let it play for a little bit. And the event, yeah, I'll play it one more time just in case. So even spaces like, for example, the staircase, right? I can set it to be more detailed than the rest. So each individual space can have its own level of resolution. And this is the final sort of structural resolution of the house. A view of the interior, how it might be utilized. So a big question is, of course, the question of fabrication. So I did 3D print everything just to test the tactility and its reaction to gravity, how it would hold up in space. So that's the first form of testing. I wanted to do a proper load test using a proper hydraulic press, but I didn't manage to get a chance to access that. Secondly, there are already very, very new forms of fabrication that could solve a lot of problems. They're being tested right now. For example, split nozzle printing that allows you to print around a sort of rebar system. Another way is sort of welding the rebar together and then using spray crate on top of that. And lastly is cast in situ formwork. So complex geometries are definitely going to be able to be produced. And so the question is what to use these complexities for. So my aim is to use it to reduce material. Finally, right now, a simplest way is to reduce these complex geometries into lines. So here I've utilized the Seagull library to sort of reduce it into a line work, a series of curvatures. And this can sort of be built, right? If we can devise them and construct them as a series of rods and nodes. Of course, we lose some of the structural complexity that's given. For example, you can see this looks like the section here looks like some of an I-beam, and then we lose the performance of that when we reduce it. But in conclusion, what my thesis was about was sort of exploring really the forefront of structural optimization tools and thinking about how architects could use it so that we could be able to think about structure, think about how to reduce material, because every line we draw means that we are utilizing material. So hopefully by doing this, it gives us new tools, right, to build better and to build using less. Yeah, thank you.
Thank you, Lip. Thank you all for sharing your thesis projects, and we have now come to the last segment of today. We will use the rest of the times for the Q&A and dialogue session too. Now we will invite our guest speakers back on the floor for the session. And again, audiences from YouTube are welcome to post your questions regarding the project or any of your thoughts in the chat box. We have already received a number of projects from the audiences to the students, presenters, and also our guest speakers. But to start with the dialogue session, I would like to ask Lip, Anders, and April, could you share with us what drove you in the respective themes of your projects? And did your project in the end turn out what you wanted it to? And also entering the more realistic architecture or design industry, how do you think your projects and personal interests can fit into the current context, or any further steps you would like to take when entering the industry? Any of you can start first.
Sorry, my microphone working?
Yeah.
Yeah, okay, good.
Yes, no.
Yeah. With regards to your question, it definitely started on food. I came into this and I knew a bit about computational architecture and everything, but I've never done it before. So this was the first time trying it. Right. And what I realized was that actually there are a lot of people writing about computational architecture, writing about all these tools, techniques, all the pitfalls that we might have. And they just all buried in old journals. Like I found writings even as far back as 1960s, and somehow nobody mentions it. So definitely there's a lot to go into. There's still a lot that I think we have to go in terms of figuring out how we can use all these computational tools and techniques in architecture. And I think also because of the complexity of it, because to understand all these things, you need to also know how computers work. You need to know how you talk to a computer. And I think that's part of the reason why a lot of firms nowadays still do not use these techniques and tools in their processes. Right? A lot of them just still stick to two-dimensional drawings, SketchUp, right? Very metric-based, Cartesian-based kind of designs, right? Because yes, the leap to get to to use this computation is quite large. It takes some time to do it. That's what I feel.
Thank you, Anders.
I think that actually, like in the future, like although now architects are still not very familiar with the new coming tools, but I believe that in the very near future, the way that algorithms work is going to really structurally change how architects approach the whole design of buildings, and it's going to change how this industry is actually functioning. So that's also the premise that I built my thesis on, but mine is more like a theoretical discussion on the social impacts of that.
For me, I think that computers are still very dumb. They're a lot dumber than we think they are. So we sort of put technology on a pedestal. But I think working with it, you sort of realize that there's a lot of problems, right? It's very hard to do. There's specific things that you need to do. So for example, we look at the stuff on Architizer or the AI generated plans, right? People have been talking, why we have no more jobs anymore. But the thing is, if you look at those carefully, they put like the doors next to toilets. It doesn't resolve things very well. It puts undesirable spaces next to each other. So there's still a very huge amount of human touch that's required, I think. So like Vignesh was saying, empathy, right? That's something that I think we need to process as we continue doing this. Yep.
Thank you all for sharing. Now we'll have some questions from the audiences on YouTube. The first question is for Yichen from Rachel Sim. She is asking that she noticed a majority of your projects are often shop interiors or other interior spaces, as opposed to the pavilion designs in many other countries. So do you think there are other opportunities, like other space or opportunities locally in Singapore to build these experimental structures and all?
Yeah, definitely. I use my live projects as a way of experimenting on material and structures. Because that's the only avenue available to me. And I think if you know, Singapore is, as a practitioner, is before you get the license to practice as an architect, your opportunities are quite limited. And to build anything in the public, the opportunities are even lesser. So I find that for smaller projects and interior projects, they became a way for me to create an oversized model of sorts, which the way I've built them, I always plan for them to be self-supporting, to be independent enough to stand on its own. And so therefore, it is always ready to be deployed, or the knowledge gained is able to be transferred to any project that are outdoors. So the thing about this way of working is that the systems then can extend itself to different type of environment, and it becomes reusable, the kind of experiment that we have done. Yeah.
Thank you for your response, Yichen. We have another question for Patrick from Rachel as well. She is asking that given this competition and given that the computational teaching itself is quite specialized, do you think like architects should get a computer science degree or to maximize efficiency or utility of computational design nowadays?
So I think I would say the strategy is that everybody would benefit from understanding, like Lip Jiang was saying, computers are very dumb, right? So but they're also very powerful. So I think everybody, it would be useful for people who, even if in their career they're not going to be writing code, if they've written code at some point in their life and understood kind of the power of it and the limitations of it. I mean, the power is that it can, you know, once you've written some kind of script, it suddenly generates all this stuff really fast, really kind of has a kind of amazing kind of scalability. And then the limitation is that every line of code is so dumb. I mean, when you first come to coding, you think like, I'll just write 2 lines of code and it'll, you know, doesn't what I have to do. I have to tell it to do every little thing. Yeah, you have to tell it to do every little thing. So I think this understanding of just how computers work at a kind of lower level is very, very useful. But in terms of the, you know, in terms of then what do you do with that? I think again, it comes, you've got to choose your poison, right? So you've got to decide what direction you're going to go in and how you as an individual are going to be competitive compared to the other individuals, whether you're an architect or whether you're anything else. So if, you know, and not everybody is going to become a coder. So some people are going to be competitive in other ways. So I don't think everybody should become a computer scientist, but you know, certainly, you know, some people will choose to get more specialized in that area. And then within an office environment, you have this huge diversity of people, even if they're all architects. But I mean, you have in an office environment, you have a lot of people who are not architects working together. But even within the architecture group, there are, you know, people doing completely different kinds of work within what falls under the umbrella of architecture. So I think everybody needs to kind of be very clear about where they're going to specialize.
Thank you, Patrick. And also for my own point of view, what I realized is that many techniques or logic that we architecture students who are interested in the field of computational design, and these techniques are actually those techniques or methodology that are already very common or advanced in some of other fields, for example, engineering, computing, or data science industries. So I was also wondering how, in our case, most of the time we will pick these skills up by ourselves or by the limited resources given by the architecture school. And then maybe there should be a more flexible or more merged curriculum for the architecture students in obtaining these knowledge sets in the future. Yeah, so that's my personal thoughts. And we have another question from Emma asking, I think this question is for Anders and also for all our speakers and presenters. Is there any thoughts on how to make these technologies less alienating and more sensitive to the types of spaces created? Or is this dependent on the scale of this, this tech is operating at?
I mean, also at the end of the day, like what Patrick said, I mean, the code, the way you program a computer is just the designer writing lines of code to tell the computer what to do. So the sensitivity really depends on the designer himself, right? And also depends on what kind of data you feed it, right? If you are not going to feed, if you're feeding it the wrong kind of data, then of course it's going to be, well, in a way, sensitive to the wrong kind of context. Right, so it depends on the designer as well as the data that you feed into the model.
Thank you, Anders. Any thoughts from our speakers?
I actually also have a question for Anders. So after having done what you have done, right? I see that you open with a very interesting question about building form, or rather the expression of the building form versus the type, meaning the internal deep structure where things are being organized. But then your project then went on to become a very outwardly driven, rather by terrain, by external environment factors, to kind of generate that few configurations that you have. And then you went on to, after that, resolve this by saying some of these units can then combine, look at how they share spaces and all that. But have you looked at like your initial question of building form versus the internal organization, or like maybe to put it simply, the way of life of these inhabitants? Because I this is my caution for myself also when I work in this field of automation and computation, is that you could create a system that would become a template for potential chaos to happen. For example, you write a system and it becomes, something that would be there for 50 to 100 years, right? How nimble is it to allow for things to be different, or choices by the inhabitants to maybe even go against the system that you have written?
Yeah, I think that's the whole point of having that digital platform, and also the whole point of having that workflow that feeds back data into the system. So really consider, okay, how do these people use space? Right? Are we making the wrong decisions when we say, okay, maybe the age condition should be a slope? Maybe the people don't want that. But without having, let's say, a first iteration, or maybe without even having the first few iterations, we don't know that, right? We don't have the data to know how these people want to live, right? And that's the whole point of the workflow, to figure out, right, how do people inhabit these spaces? What are patterns? And then we take that data, feed it back into the design process to understand how can we really craft spaces that are more sensitive, right? Without data, we can't do that.
Okay.
May I also check whether like Patrick, Vignesh, or Yichen has any other comments on our students' work for Lip, Anders, and April?
Absolutely. I was actually waiting someone would ask that. I'm blown away by Anders, Zhu, and Lip Jiang's work. I'll be honest with you. I'm blown away by the storytelling, the narration, the fluidity of your graphics, your thinking, and application of computational thinking, basically, right? What I would probably say is, don't worry too much about the output you have produced, because that will keep changing. Like when you come into the industry, when you start to work with clients, when you start to work with multiple stakeholders, all that will change. But what's unique about what you presented is your storytelling, and that's beautiful, and it comes across as very sophisticated, with a lot of thought given to application of computational thinking, which is very important, and I absolutely loved it, and it kind of inspired me a lot as well. So they are absolutely beautiful, right? And I mean, to answer, I think Yichen's question, and somebody else from the audience as well, right? Our industry is a highly fragmented industry, okay? Unlike automobile or unlike aeronautical industries, right? Where you take a company like Boeing, right? The first line they put on the CAT program to the final delivery of that entire airplane to Singapore Airlines, they control the entire supply chain, right? Same way with Tesla, same way with Ford, or any automobile, for example, right? So their way of using technology for immediate application to mass, for mass usage is much more higher than what, as architects, our scope and our effect on the building industry is. Because honestly, architects are only the first 10 to 20% of the entire chain, and then there are so many players after us that take the whole project. I mean, we can design all this on paper. Somebody has to bankroll this project to even get it built in the first place, because we are not the ones building them, right? So if you consider all this, the best way is for architects to be technologically advanced, even if you're not the one writing the code, if you encourage people to work in such a fashion, if you have people in your team who are very good at it and you leverage their skills, what happens is that this has a knock-on effect to stakeholders that comes after architects. So like you've got engineers, you've got fabricators, you've got construction people, you've got facility managers, you've got operators. All of them are in the chain of the building industry. And all this has a knock-on effect on each one of them, right? So that is why it is very important for architects to be cutting edge in whatever they are doing, because that's the only way we can transform this industry.
Thank
Maybe
you.
maybe I can jump in with a few comments also. I think one of the I think for all the three thesis projects that were presented, I mean, I think it's very interesting that they are all sort of directly trying to deal with scalability. And I think this is like a really different kind of thesis than many of the theses well, you know, let's say 10 years ago at NUS, you know, lots of theses were, you know, a one-off project, a one-off building. And here we have three theses that are all looking at something that kind of can replicate and expand and scale, you know, it's trying to tackle the whole idea of design in a different way. And I think that's, I think the scalability is such a interesting dilemma, that the problems that we're facing of climate change, of social inequity, all these kinds of issues are all only solvable with solutions that are scalable. So if you look at SDE4 as a kind of net zero energy building, it's great, but if it's not scalable, it's irrelevant. I mean, if you can't make hundreds of millions of those buildings very quickly, it doesn't help, because the issue of climate change is not to have one example building. It is a question of how do you transform the whole building stock. So, and the same with you know, social problems and all these kinds of problems is scalability. So I think it's kind of interesting that the three theses are looking at this at processes rather than kind of a single outcome. And I think this will translate, I mean, once you get into practice, of course, it's completely different. The kinds of things that you'll be doing have to be really much, you know, are so grounded in the limitations of real life. But the issues of scalability will still be there. I think, you know, practice is trying to figure out how to make their processes more scalable and how to work in a different kind of way. I think, you know, in the Singapore context also, I think what Vignesh was saying, you know, we've got this BCA of, you know, been pushing BIM and then VDC and IDD. And so, you know, this IDD process is really this ecosystem of contractors, fabricators, subcontractors, developers, operators, all these people connected in a digital chain. And just, I was a jury member on the IDD Awards recently. And so it's really interesting to see how advanced the contractors are. The contractors are actually digitally more advanced in general than the architects. And they're really pushing it because for them, it makes such a huge difference to their bottom line, obviously, because if they can avoid having to, you know, knock down a piece of concrete that happened to be in the wrong place, then that's going to save them a lot of money. So, I mean, for them, the digital, you know, investing in this digital ecosystem is really worth it. I think the architects are sort of in there, but not really leading at the moment. And the developers and operators are the ones who are really going to benefit, because they're the ones who are going to be running the building for 20 years, and they're the ones who are going to really benefit from, you know, a lot of this digital integration. So I think in this new kind of reality of everybody's struggling, trying to figure out new processes, new ways of exchanging data, how to make this whole process more efficient and more scalable. I think that's going to be very interesting. And I think the skills that the thesis students have developed are going to be very transferable, not in a direct way, but in an indirect way. I think it's going to be very transferable.
Thank you, Patrick. We are near to the end of our dialogue session, so maybe we'll address one last question posted by Zhikai. A question for everybody also, like to get everyone's comments. How can computers be a tool to integrate data that is not quantifiable but impacts the design output? Some examples being user satisfaction, culture shifts, etc.
Maybe I can take a shot at it very quickly so we can end the session. I think the main thing is it can't be done because of data privacy issues. So things like that. The main thing about data is that you must have data mining somewhere. So companies like Google are very good at that because they can take your info from Google Maps, they can take your info from all that. So it's mainly working with tech companies and maybe like tracking stuff on their apps and stuff. Satisfaction levels, 5-star reviews on certain apps. That's a way to do it. But of course, the privacy laws here, that's a very big problem. As a student, of course, there are ways, you could implement surveys, you could have apps that you send to people, but adoption is going to be a huge problem. Yeah. Any comments before we close up?
Actually, maybe a personal comment from myself. Like, I feel that as computational design tools and techniques get more advanced, they provide us with the opportunity to not only generate optimized design results, which is about like the usual quantifiable features such as ecological properties or buildability. And actually currently from my reading that a lot of similarly qualitative features, for example, user friendliness, workability or imaginability. So these kind of features are now getting measurable with all like with, let's say, things like behavioral studies, which measures users' various cognitive reactions towards design details, etc. So I guess in the future, many things will get more data and like more and more data driven and measurable by all. But eventually, of course, we still have the question of whether like architects' own personal judgments or like assumptions and empathy still can take place in the future.
Yeah, I think that question was somehow also answered in April's project, where I think what I've seen is more like a rewriting of what, or kind of replacing the monetary system with something else, with a credit system, or with green credit or whatever. I think with that, then with the answer of who funds the project, how the project is funded, how the building come into being, will be a lot more complex, and that may allow for new technologies to intervene earlier on in the process. Yeah.
Well, I mean, I love this question for two reasons. The first one is it tries to understand what are the non-tangible in that sense. How do you measure the non-tangible, right? And how do you have data for it? Number two is I think there could be biases in the data, just like how humans carry cognitive biases. We carry biases based on gender, race, and all this, and we are constantly learning to be in a society to get rid of our biases. But sometimes even in our digital avatars, you can see all these unnecessary arguments in YouTube comments, right? And people kind of losing their sense and then kind of chatting away. And assuming if all this data is kind of, if a computer is able to read all this and is able to create an opinion of all this, right? Imagine how biased that would be, right? And this has come about in a lot of different cases in the US where the current state of data is actually against blacks. So the computer is more likely to actually assume that a black person is a criminal than probably what is not the case in real life, right? So this data biases is everywhere, and as anyone who's computationally inclined one of the first things you got to do is to make sure that the data is right, it is believable, it represents all sections of the society. Like look at all the election analysis, right? They get it wrong all the time because they're getting this sometimes from Facebook or other digital means of access that a certain section of the society are not there. They're not using it. So to kind of take that data and make it the right opinion backfires like crazy, right? And honestly, some of these tools like Facebook also polarizes opinions. You're either on this camp or you're on that camp. You can't have a neutral opinion sometimes, right? So we got to be. I mean, I'm just putting a caveat there to say that yeah, data-driven decisions, all this is good, but your decisions are only as good as the data, right? So you got to be very sure to make. I mean, you got to be very diligent in making sure the data that you're using is kind of gotten rid of all those biases.
I might add just to that, maybe. So I think one thing which one of Vignesh's first slide he showed was this figure of 8, where you have, you know, what's the computer good at and what's the human good at. And so I think when you start talking about these non-tangibles, you also have to really question whether we should be trying to make them quantifiable, in the sense that that's all we're good at, right? Why would we automate that bit? That's what we're good at. We're not good at running simulations in our head, but we're quite good at evaluating whether we believe something is good for society or not. So I think we should question those things and really decide, you know, if we're going to automate stuff, we should automate the stuff that we're not good at and try and keep the rest to ours in our camp, right? And I think the other thing is with data is that, you know, one thing from COVID is that data is, you take data from the past and extrapolate to the future. Now, you know, if at the end of 2019, you gathered 10 years of data about life in a city, right? And then you said, well, in 2020, life in the city is going to be like this, right? Because on December 2019, you had all this data. And, you know, 2020 turned out to be a bit different, right? You know, life in the city was very different. And I think, you know, with climate change, with social inequity, with all the problems that we are kind of facing, life in this future is going to be, whether, you know, for better or for worse, is going to be very, very different from the past. So I think, you know, data-driven decision-making is also very, very dangerous in that sense, because it assumes that the world is there's a kind of status quo, and this if there's one thing we know is that there's no status quo anymore. I think the future is different.
Thank you, Patrick. Any last comment from our speakers or presenters? If not, we have now come to the end of our forum. For more questions from the audiences, you are welcome to post your questions on the comment in YouTube or email us, and we will try to bring these questions to our guest speakers as well as student presenters and get back to you all. And so we would like to say thank you again to all our guest speakers, Dr. Patrick Jensen, Mr. Pan Yi-Chen, and Mr. Vignesh Kaushik, as well as our student speakers, Anders Ang, April Zhu Weijie, and Li Lip Jiang, for the informative talks and dialogues, and also to the audiences for your participation. Please visit our website on nusmmarkgradshow.com/2021 for more information on the events. And our next forum will be tomorrow, 18th of July from 4 p.m. by the History and Heritage Cluster. So thank you very much. Stay safe and have a great evening.
Thank you.
Thank you. Thank you.
Thank you.
Thank you.
Thank you.
Eileen, are we offline?